if we wanted to understand global power back in the 20th century, we'd look at maps, right? Maps showing oil fields, steel mills, shipping lanes, that kind of thing.
Yeah, the physical sinews of industrial might.
Exactly. But today, to really grasp power, you have to look at something almost invisible. Super, super small. The semiconductor chip.
It's fundamentally shifted. It really is the new copper, the new iron, the new oil, all rolled into one tiny package.
And that shift is just profound. So today, we're diving deep into Chris Miller's fantastic book, Chip War, The Fight for the World's Most Critical Technology.
It's a brilliant work. It really traces how this thing, the integrated circuit, which at its core is just a sliver of silicon, became the absolute bedrock of our entire digital world.
Everything we do online, right? Every email, every search, every transaction, it's all just vast strings of ones and zeros.
And those ones and zeros only exist, only get processed because of billions, literally billions of microscopic switches, transistors etched onto that silicon.
Our mission here is to track that incredible journey. We're going from its origins in Cold War military labs
Driven by necessity.
through decades of really intense global competition, right up to the present day, where we have this kind of geopolitical pressure cooker, the most advanced chip making. It's concentrated on one small, very contested island.
Which is an incredibly precarious situation when you think about it.
Totally. So maybe let's set the scene. Contrast the old way of war with the new. You mentioned WWII earlier, massive industrial attrition.
That's the perfect baseline, yeah. Think about it. The Allies won WWII largely because they could just churn out more tanks, more planes, more ships. It was about volume, industrial output.
Okay, now compare that today. Miller uses the example of a modern warship, like the USS Mustin operating in the Indo-Pacific.
Right. And when you analyze its power, you're not counting tons of steel in the same way. You're counting processing power. You're counting network speeds, precision.
So the ship's ability to, say, project power or defend shipping lanes, it relies entirely on microelectronics.
Completely. It's a massive technological leap. Those sailors are dealing with just floods of incoming data streams simultaneously, from satellites, from drones, from other ships, allied aircraft.
All processed in real time.
All processed in real time by advanced microprocessors. The goal isn't just overwhelming force anymore, it's surgical precision. That ship carries missiles in vertical launch cells that can hit targets hundreds of miles away with astonishing accuracy.
And that accuracy comes from the chips guiding them.
Exactly. That fundamental shift from needing sheer industrial might to needing silicon-enabled precision, that's why the chip is now the single most critical piece of technology underpinning global power, both economic and military.
Okay, so to really appreciate that shift, we need to rewind. What did computing look like before the chip? What were the bottlenecks that engineers were desperately trying to solve?
The pre-chip era was all about limitations. Speed, size, reliability, they were all huge problems. First off, you had manual calculation, actual people doing the math.
Human computers?
Literally. During the Great Depression, the Works Progress Administration had this thing called the Mathematical Tables Project. Employed hundreds of people, mostly women actually, just to sit there and manually calculate logarithms, trigonometric functions, really complex stuff.
And they published the results.
Yeah, in these huge, dense volumes, 28 of them. If you needed a specific value, you had to physically find the right book, flip through the pages. That was high-speed computation back then.
And the attempts to automate this mechanically, especially for things like warfare, they weren't exactly hitting the mark, were they?
Oh, they were shockingly inaccurate. Miller talks about the famous American bomb sights used in World War II. These were intricate mechanical devices, right? Crews spun dials for wind speed, altitude, ground speed.
Trying to calculate the trajectory.
Trying, yes. But they only considered a few variables and relied on perfect human operation under incredible stress. The result, terrible accuracy. Over Germany, something like only 20% of American bombs landed within 1,000 feet of their target.
So victory came through sheer volume, dropping thousands of bombs hoping some would hit.
Exactly. Quantity over quality. Because the quality just wasn't technologically possible yet.
Then came the attempt to use electricity instead of gears. But that ran straight into the problem of vacuum tubes.
Ah, the vacuum tube. The first electrical switch. It was basically like a biggish light bulb, a glass tube with a filament inside. You could switch it on for a 1 or off for a 0. Binary logic.
But they were huge and unreliable.
Massive.
Yeah.
And power hungry. The famous ENIAC computer from the 1940s, it used 18,000 of these tubes, weighed 30 tons, took up a huge room, like 1,800 square feet.
Ah.
And it sucked down so much electricity, people said it dimmed the lights in Philadelphia when they switched it on.
Oh.
Plus, the tubes failed constantly. On average, one burned out every couple of days. The machine was almost never running at full capacity.
So clearly engineers needed something better, something solid state. No moving parts, no burning filaments, no massive size. Which brings us to Bell Labs in New Jersey.
Right, and specifically to William Shockley. Brilliant physicist,
Mm.
visionary. Also, according to Miller and others, notoriously difficult. Obnoxious is the word used.
Okay, but brilliant?
Undeniably. He was obsessed with controlling electricity flow in solid materials, semiconductors like silicon, using an electric field, his solid-state valve idea.
He tried an experiment.
In 1945, yeah. But he was looking for this tiny electrical effect, and his instruments just weren't sensitive enough. He couldn't measure anything. Wrote it off, nothing measurable. He actually thought his theory was wrong for a while.
It's amazing how close he was, but the tech wasn't there yet. So the actual breakthrough, the transistor, it wasn't solely his invention in the end.
It was complex. Others at Bell Labs, like Bardeen and Bratton, made key experimental progress on the point contact transistor. But Shockley, building on that, conceptualized the more robust junction transistor, which became the standard. His core idea, the three-layer semiconductor structure, was the winner.
Explain that concept simply. How does it work as a switch?
It's elegant, really. You have 3 layers, or chunks, of semiconductor material. You apply a tiny electrical current to the middle layer. That small current controls whether a much larger current can flow across the whole device. So, tiny input controls big output, on-off, a solid-state switch. No heat, no burnout like a vacuum tube.
Okay, so the transistor is invented, it works. But how does it go from a lab curiosity to something that changes the world? What lit the fire under it?
2 words. Cold War,
Yeah.
specifically the U.S. military. The real catalyst, the moment everything changed, was the Sputnik shock.
October 1957, the Soviets launched the first satellite.
Exactly. And it absolutely terrified Washington, a massive crisis of confidence. Suddenly, there was this desperate, urgent need for smaller, lighter, more reliable electronics for rockets, for missiles, for guidance systems. The Department of Defense basically became the first big customer, demanding these new solid-state devices.
And the Apollo program, getting to the moon, that put incredible pressure on miniaturization, too.
Oh, massively. NASA and MIT were tasked with building the Apollo guidance computer. It had to be small enough, light enough, and reliable enough to navigate a spacecraft to the moon and back.
What were the initial projections like?
Even using individual transistors instead of vacuum tubes, early estimates said the computer would need to be the size of a refrigerator, and it would consume way too much power for the spacecraft. It seemed impossible.
Until the integrated circuit came along, putting multiple transistors on one chip.
That was the only way forward. It solved the size, weight, and power problem all at once. So companies just starting up, like Texas Instruments and Fairchild Semiconductor.
The pioneers of Silicon Valley.
Right, they weren't just tinkering, they were making components vital for national security, for winning the space race. TI's first really big order for integrated circuits. It was for the guidance computer on the Minuteman II nuclear missile.
So military demand really bootstrapped the whole industry, gave them the contracts to figure out mass production.
Absolutely. Without that Cold War imperative, the chip industry we know today would have developed much slower, if at all, in that form.
But even with all that guaranteed military money, some people saw a bigger picture. Robert Noyce at Intel, for example.
Noyce was a visionary in terms of scale. He understood something crucial. Military contracts were high value, sure, but low volume. To really drive down the cost per transistor, to make Moore's Law happen, you needed massive volume, and that meant civilian markets.
He deliberately targeted the mass market.
He did. His logic was simple. If a chip is reliable enough for a missile, it's definitely reliable enough for, say, a calculator or a hearing aid. He famously pushed back against relying solely on government R&D funding, called it like putting venture capital in a savings account.
Huh, that's a great line.
And he said, venturing is venturing, you want to take the risk. He saw the huge potential, the infinite market, if they could just make chips cheap enough for everyday consumers.
And Miller gives that great example of the Zenith hearing aid.
Yeah, it perfectly illustrates the point. The chip inside one of the first really small popular Zenith hearing aids. It was originally designed for a NASA satellite. They just repurposed it.
So the military paid for the cutting-edge development, and then companies like Intel figured out how to scale it for everyone else.
Exactly. Noyce knew consumers were price sensitive. But if you could take a transistor that cost maybe $500 in 1958 and eventually get it down to fractions of a cent, The world would beat a path to your door. And that's exactly what happened.
Okay, so Silicon Valley is booming, fueled by defense needs and this burgeoning consumer vision. But the knowledge isn't staying contained within the US, it starts to spread.
And the first major wave of competition comes from Japan. This wasn't accidental, though. The U.S. occupation after WWII actively helped transfer technology to rebuild Japanese industry.
So they were sharing transistor knowledge.
Yes. Miller quotes Japanese physicists like Makoto Kikuchi talking about how incredibly exciting it was to get their hands on American technical publications, like the Bell System Technical Journal. He said his heart would pound seeing the words semiconductor or transistor. They knew this was the future.
And Japanese companies became masters at taking this core tech and turning it into killer consumer products.
They really did. Sony is the prime example. Akio Morita, Masaru Ibuka, they pioneered things like the transistor radio, later the Walkman. They took the basic technology, but focused relentlessly on quality, design, user experience.
And in doing so, they shattered the old image of made in Japan.
Completely. Before Sony, made in Japan often meant cheap, low-quality copies. Sony proved that Asian firms could not only compete, but win in high-value, high-tech consumer electronics. It was the first real challenge to American dominance in this new field.
Meanwhile, back in Silicon Valley, the relentless pressure of Moore's law, doubling density, halving costs, was creating huge pressure on the manufacturing side, specifically on labor costs.
The economics were just brutal. Making the silicon wafers the initial fabrication, that required expensive clean rooms, highly skilled engineers, high wages. But the next step, the assembly attaching tiny gold wires to the chips, putting them in their plastic packages, that was very labor-intensive, manual work.
And the company leaders were looking to cut costs there.
Aggressively. Miller highlights figures like Charlie Spork at Fairchild. He was apparently dead set against unions, saw them purely as an obstacle to efficiency and cost-cutting.
And the workforce doing this assembly?
It was largely women. The book points out that management at the time often believed women could be paid less, were less likely to organize, and maybe offensively. But it was the perception had smaller, more nimble hands for the delicate work of bonding those tiny wires.
But even those relatively lower domestic wages weren't low enough to keep pace with the cost reductions needed.
No. Not if you wanted to hit the price points Moore's law demanded for mass adoption. So the American firms started looking overseas aggressively.
This is the beginning of offshoring in electronics.
Absolutely. The birth of the modern global electronic supply chain. Fairchild really led the way, but TI, Motorola, they all followed quickly. They started chasing cheaper labor across Asia.
Where did they go first?
It was like a relentless hopscotch for the lowest wage. Miller tracks it. Started in Hong Kong, maybe 25 cents an hour in the mid-60s, then shifted to Taiwan, 19 cents, then Malaysia, 15 cents, Singapore, 11 cents, South Korea, just 10 cents an hour.
Wow. So the core design, maybe the initial wafer fab, was still in the U.S.?
Often, yes. But the labor-heavy final assembly and packaging, that moved across the Pacific at speed.
Now, this offshoring had really interesting strategic implications, especially in a place like Taiwan. It wasn't just about jobs for them.
No, it was seen as much more. K.T. Lee, a key figure in Taiwan's economic planning, saw hosting, say, a Texas Instruments assembly plant as a form of security, statecraft through supply chains.
What was the thinking?
His logic, as Miller describes it, was pretty clear. If American companies have major investments, hundreds of millions of dollars tied up in facilities on Taiwan, and rely on those facilities for ongoing revenue, then the U.S. government would have a much stronger incentive to defend Taiwan if it faced threats from mainland China.
So the factories became like economic hostages in a way, anchoring U.S. interest.
Yeah, an economic link that strengthened the security relationship. Lee Kuan Yew in Singapore had a similar perspective. Integrating into these vital global supply chains was crucial for their own security and stability.
Okay, so the supply chain gets globalized, assembly moves to Asia. But then, in the 1980s, the competitive threat shifts back from consumer goods to the core technology itself. Japan mounts a major challenge in memory chips.
This was the DRAM war. Dynamic random access memory, the basic working memory computers need. Japanese companies Hitachi, Toshiba, NEC, they just poured money into DRAM. By 1985, Japanese firms accounted for something like 46% of all global capital spending on chip manufacturing equipment. And critically, they weren't just spending more, they were making better chips.
Better quality.
Yeah. American companies like Hewlett-Packard, who were big customers, started doing their own quality checks. And the reports came back consistently. The Japanese DRAM chips had lower failure rates. They were simply more reliable.
Ouch. How did the American companies react to that? This was an existential threat.
They were reeling. Their main response was to cry foul, blaming Japanese government subsidies, protected domestic markets, maybe dumping practices where chips were sold below cost internationally. They pointed to NTT, the giant Japanese telecom monopoly, which bought almost exclusively from Japanese suppliers, giving them a huge guaranteed market.
Did the U.S. firms sue?
Oh yeah, there were anti-dumping lawsuits, trade friction. But despite all that, Japan's market share in DRAM just kept climbing. It pushed many of the original Silicon Valley memory pioneers towards bankruptcy. It was a genuine crisis for the U.S. chip industry.
That crisis really forced a moment of truth at Intel. Andy Grove, the CEO famous for his intensity, having survived the Nazis in Hungary, he knew they couldn't just keep doing what they were doing.
Right. Intel was built on memory chips, on DRAM, but Grove looked at the Japanese onslaught, the quality, the scale, the lower costs, and realized their fundamental business model was broken. He had this famous internal debate.
The one where he asked Gordon Moore, his co-founder.
Exactly. He asked Moore, if we got kicked out and the board brought in a new CEO, what do you think he would do? And Moore, after some hesitation, apparently said he would get us out of memories.
And Grove's response.
Why shouldn't you and I walk out the door, come back in, and do it ourselves?
Yeah.
It was this exercise in what he called constructive confrontation, facing the brutal reality.
So they decided to abandon DRAM, the thing that made them famous?
It was an incredibly gutsy gamble. They decided to completely exit the memory business, which was their main revenue stream, and bet the entire company's future on microprocessors, CPUs, the brain chips, for the emerging personal computer market.
Which was still pretty new territory back then.
Very much so. But Grove saw the potential. He enforced this ruthless focus on the CPU, particularly their 86 architecture. His management style was legendary, intense, paranoid. His motto became, only the paranoid survive.
And the bet paid off.
Massively. That pivot, combined with the incredible success of Microsoft Windows running on Intel's x86 chips, it gave Intel a near stranglehold on the PC market for decades. It saved the company and cemented Grove's legacy. They avoided the fate of so many other U.S. memory makers.
While Intel was making this huge internal shift, focusing on designing and manufacturing its own CPUs, something equally revolutionary was starting up in Taiwan, something that would completely reshape who builds chips versus who designs them.
Yeah, this is where Morris Chang enters the picture, a real giant in the industry. He was a longtime veteran of Texas Instruments, and with significant support from the Taiwanese government, he founded TSMC, Taiwan Semiconductor Manufacturing Company.
And his big idea was the Foundry model.
The pure-play foundry model, this was radical. See, before TSMC, the assumption was if you designed chips, you also had to build them in your own factories, your own fabs. Like Intel did. It was vertically integrated.
What did Chang propose instead?
TSMC made a simple, powerful promise. We will only manufacture chips for other companies. We will never design our own chips to compete with our customers. Pure manufacturing services.
Why was that promise never competing so important?
It changed everything. Building a state-of-the-art fab costs billions, now tens of billions of dollars. It's incredibly capital-intensive. By guaranteeing neutrality, TSMC removed a huge barrier. It allowed a whole new type of company to flourish. The Fabless design house.
Companies that only design chips, they don't build them.
Exactly. Think NVIDIA, Qualcomm, AMD in its current form, Broadcom. These companies could focus all their energy and capital on chip architecture, on the blueprints, the intellectual property. They became the authors, and TSMC became the printer.
So it democratized chip design in a way.
It really did.
Yeah.
You didn't need $10 billion for a fab to innovate in silicon design anymore. But here's the paradox.
While design spread out, the actual manufacturing got more concentrated.
Precisely. The sheer economics of chip manufacturing, the need for massive scale, the latest, most expensive equipment, meant that only a few players could really compete at the cutting edge. So, manufacturing consolidated, even as design proliferated.
And TSMC, because they were first and executed brilliantly.
They ended up dominating advanced logic chip production. Miller calls it the monopolization of the digital printing press. It made TSMC absolutely indispensable, a critical node in the entire global tech ecosystem.
Okay, so the way chips are made is changing. And the types of chips being designed are also starting to shift, moving beyond just the general-purpose CPU that Intel mastered.
Right. We start seeing the rise of specialized silicon. A key example is NVIDIA, led by Jensen Huang. They bet big on graphics processing units, GPUs.
Initially for video games, right, making realistic 3D graphics.
Exactly. Now, GPUs work very differently from CPUs. Intel CPUs are amazing at doing complex tasks one after another, sequentially. Very fast. But GPUs are designed for parallel processing. They can do thousands, even millions of relatively simple calculations all at the same time.
Like calculating the color of every pixel on a screen simultaneously.
The perfect analogy. And it turned out that this parallel architecture, initially designed for graphics, was accidentally the perfect tool for something else entirely.
Artificial intelligence.
Bingo. Researchers, PhD students, they realized that training AI models, which involves feeding them massive amounts of data, like millions of images to recognize a cat, could be done way, way faster on GPUs.
Because the GPU could process lots of data points at once, in parallel.
Exactly. Instead of feeding images one by one to a CPU, you could process batches simultaneously on a GPU. It dramatically cut the time and the cost needed to train the huge AI models that underpin everything from ChatGPT to self-driving cars today.
And then there's Apple. They also decided standard chips weren't good enough. They needed their own silicon.
Yeah, Steve Jobs saw this early on. Apple realized that to get the kind of seamless performance and battery life they wanted for their products, they couldn't just rely on off-the-shelf chips from Intel or Qualcomm. They needed to control the silicon itself.
So they started designing their own.
They bought a small chip design firm called PA back in 2008, hired top talent, and invested heavily. The first big result was the A4 chip in the original iPad and iPhone 4.
And that commitment to custom silicon continues today, right? Even in their Macs now.
Absolutely. From the A-series chips in iPhones to the M-series and Macs, even custom chips for AirPods. That deep integration of hardware and software, enabled by designing their own specialized chips, is arguably the core reason Apple's products feel so smooth and perform so well.
Which brings us back to that label on the back of the iPhone. It's misleading, isn't it?
It really is. Designed by Apple in California, assembled in China. It sounds simple, but it hides the most critical, most complex, most irreplaceable part of the equation. The actual fabrication of the brain of the phone, the application processor, that cutting-edge chip. It can only be made in those giant, hyper-advanced foundries in Taiwan, primarily by TSMC or maybe Samsung in South Korea. The most vital component relies entirely on manufacturing capabilities that are now concentrated across the Pacific.
Okay, so while the US, Japan, Taiwan, Korea are building this incredibly complex, efficient, but also concentrated global system, what about the other superpower? The Soviet Union. They obviously understood the military importance. How did they try to compete?
They understood the importance, definitely, but their approach was fundamentally flawed, shaped by their command economy and their past successes in espionage, particularly with nuclear weapons.
They thought they could just steal the technology.
Basically, yes. Miller recounts this telling story about a top Soviet official, Alexander Shokin. He literally ordered his engineers to take a specific Texas Instruments chip, the SN51, and copy it. One for one, without any deviations, was the order, and he gave him a crazy deadline, like 3 months.
Just reverse engineer it and make their own.
That was the plan. They figured, hey, espionage worked for the atomic bomb, it'll work for chips.
But it didn't work. Why not? Chips are different.
Fundamentally different. Miller uses the analogy. Copying a finished cake doesn't give you the recipe, the baker's technique, or the specialized ovens needed to make it consistently.
You need the whole process, the ecosystem.
Exactly. The Soviets could maybe analyze the chip's layout, but they lacked the entire industrial ecosystem required for high-volume, high-yield production. They didn't have the ultra-pure chemicals, the specialized gases, the incredibly precise optical equipment. And crucially, they lacked the tacit knowledge, the know-how.
What do you mean by know-how?
The unwritten stuff, the specific temperatures, the exact timings for chemical baths or light exposure. The tricks engineers learned through experience and iteration. People like Andy Grove knew this stuff was often passed down engineer to engineer, not written in manuals. It's process knowledge, not just product knowledge. The Soviets couldn't just copy that.
And there was another huge problem for them, Moore's Law itself.
Yes. This was almost a built-in defense mechanism for the West. Moore's Law meant chip technology was advancing at this relentless, exponential pace, doubling transistor density roughly every 2 years.
So even if the Soviets managed to copy a chip,
By the time they figured it out, reverse engineered it, and maybe got a production line working, the chip they copied was already obsolete. The West had moved on to the next generation, or the generation after that.
they're always playing catch-up and falling further behind.
Precisely. Their whole system, secretive, top-down, defense-focused, was the exact opposite of the iterative, competitive, market-driven culture of Silicon Valley that fueled Moore's Law. They were doomed to be perpetually backward in semiconductors.
This technological gap wasn't just an economic issue, it became central to U.S. military strategy against the Soviets, the offset strategy.
Right. This was driven by Pentagon thinkers like Andrew Marshall and Bill Perry. They looked at the Cold War balance sheet and saw the Soviets had a huge advantage in conventional forces, more tanks, more troops, more artillery, a quantitative edge.
The U.S. couldn't compete on numbers alone.
Probably not,
Yeah.
or at least it would be incredibly expensive. So the offset strategy was about using technology to negate that numerical advantage. They pushed for massive investment in things like precision-guided missiles, stealth aircraft, advanced sensors, and communication systems, all enabled by cutting-edge microprocessors.
Using silicon to beat steel, essentially.
That's a great way to put it. The idea was to make Soviet investments in huge tank armies less relevant by being able to destroy them accurately from afar. It also forced Moscow into a ruinously expensive arms race, trying to counter technologies they simply couldn't replicate domestically.
And the first major real-world test of this silicon over steel doctrine came in the 1991 Persian Gulf War.
That war was a stunning demonstration. It really became known as the triumph of silicon over steel. Things like the Paveway laser-guided bombs, which had Texas Instruments components inside.
They were incredibly accurate compared to older bombs.
Night and day. Air Force studies showed that aircraft using these precision munitions hit something like 13 times as many targets compared to planes dropping unguided dumb bombs. The images on TV looked almost like a video game targets destroyed with pinpoint accuracy. It paralyzed the Iraqi military, which had a lot of Soviet equipment.
And the message wasn't lost on the Soviets themselves.
Not at all. Miller mentions Mikhail Gorbachev visiting Silicon Valley around that time in 1990. He saw the dynamism, the innovation, and reportedly said, "The ideas and technologies of tomorrow are born here in California." He knew their system couldn't keep up. Many argue this technological gap was a key factor in the collapse of the Soviet Union. The Cold War was over, and in many ways, Silicon Valley had won.
But that victory and the relentless drive for efficiency that created the global supply chain ironically set us up for our current vulnerability. These incredibly specialized, irreplaceable choke points.
Yes. The system became hyper-efficient, but also hyper-concentrated and brittle. And the single most critical choke point today is in manufacturing the machines that make the most advanced chips, specifically lithography machines.
The machines that print the circuits onto the silicon wafers?
Exactly. And for the cutting-edge chips today, the ones with features measured in just a few nanometers, literally a few dozen atoms wide, you need a specific type of lithography called extreme ultraviolet, or EUV.
EUV, why is that so difficult?
Because EUV light has such an incredibly short wavelength, which you need to print tiny features. But that short wavelength also means it gets absorbed by almost everything, even air. So the entire process has to happen inside a near-perfect vacuum chamber.
Okay, vacuum chamber. How do you make the EUV light inside the vacuum?
This is where the engineering becomes almost science fiction. It involves firing incredibly powerful custom-built lasers.
Lasers made in Germany, right?
Yeah.
By Trump.
Yes, these gigantic carbon dioxide lasers. Miller notes one model has over 457,000 individual component parts. These lasers fire rapid pulses, 50,000 times a second, at tiny droplets of molten tin that are falling inside the vacuum chamber.
Hitting falling drops of tin with a laser 50,000 times a second.
Precisely. Each laser strike vaporizes the tin droplet into a plasma, which emits the exact frequency of UV light needed. That light is then collected by incredibly complex mirrors made by Zeiss in Germany and focused onto the silicon wafer to print the circuit pattern.
The complexity is just staggering. And these machines cost
well over $100 million each. Probably closer to $150 million or more now for the latest generation. They are the most expensive mass-produced tools in history.
And only one company in the world makes them.
Only one company has mastered EUV lithography, the Dutch firm ASML. And interestingly, Miller points out ASML succeeded where Japanese rivals failed, partly because they didn't try to do everything in-house. They orchestrated this incredibly complex global supply chain.
So, U.S. provides the light source technology from Cymer, which ASML acquired.
Germany provides the unique lasers, Trump, and the even more unique reflective optics, Zeiss.
And ASML in the Netherlands integrates it all into these monstrously complex machines.
Exactly. So the paradox is, while we talk about globalization, the most critical manufacturing technology hasn't really diffused. It's become monopolized by a tiny handful of irreplaceable companies in just 3 or 4 countries, all dependent on each other.
And no one else can easily replicate this. Not the U.S., not China.
Not easily, and certainly not quickly. Building that ecosystem of suppliers, mastering the physics, perfecting the engineering, it took ASML and his partners decades and tens of billions in R&D. It's an incredible barrier to entry. And that makes ASML's EUV machines the ultimate geopolitical choke point. If you don't have access to these tools, you simply cannot make the most advanced chips, period.
Which brings us right back to Taiwan, because that's where most of these incredibly expensive ASML machines are actually located and operating, inside TSMC's giant fabs.
Right. The concentration is just stunning. The vast majority of the world's most advanced logic chip manufacturing, we're talking chips below 7 nanometers, heading towards 3 or 2 nanometers, happens in Taiwan, overwhelmingly by TSMC, with Samsung and South Korea being the only other major player at the leading edge.
And this includes the chips critical for defense.
Absolutely. Everything from the processors in an F-35 fighter jet to the chips needed for advanced AI, surveillance systems, supercomputers. The U.S. military, like the entire global economy, is functionally dependent on fabs located in Taiwan and South Korea.
And Taiwan sits, what, about 100 miles off the coast of mainland China? Within easy range of missiles.
It's the central geopolitical fault line of our time. Beijing considers Taiwan a rogue province and has explicitly refused to rule out using force to achieve unification. The concentration of TSMC's irreplaceable fabs makes the island an even greater strategic prize.
What would happen if there were a conflict? Or even just a blockade?
The disruption would be catastrophic. Miller argues, and most analysts agree, that even a limited disruption, say, a blockade preventing ships from reaching Taiwan, or a single missile strike taking out a key TSMC facility would instantly cripple global industries. Cars, smartphones, computers, cloud data centers, medical equipment, everything would grind to a halt. The economic damage would likely run into the trillions of dollars, far exceeding any recent financial crisis.
And Chinese strategists are aware of this vulnerability.
Oh, completely. Miller cites Chinese government analysts openly arguing that controlling TSMC is a strategic necessity for Beijing. One quote was stark: "We must seize TSMC." They see both as a way to secure their own supply and deny it to the West, particularly the U.S.
So given this growing risk, how did the U.S. let so much critical manufacturing capacity drift offshore? For decades, the policy seemed to be just hope for the best.
Yeah. Miller characterizes the prevailing Washington consensus for many years as the run faster delusion. The idea was rooted in globalization theory that technology inevitably diffuses, supply chains will naturally optimize for efficiency, and the U.S. just needed to stay ahead in innovation in design. Manufacturing was seen as less important, almost like a commodity.
The assumption was, we design it here, they can build it cheaper over there, and that's fine.
That was largely the attitude. There were warnings, though. Miller mentions analysts like Richard Van Atta warning back in 2007 that U.S. technological leadership would erode seriously because advanced manufacturing was moving abroad. But the dominant view was that this globalization of fabs was efficient and inevitable.
But it wasn't really globalization, was it? It was concentration.
Exactly. It wasn't spreading out everywhere. It was concentrating very specifically in Taiwan and South Korea.
Right now.
So globalization was really Taiwanization plus Koreanization at the leading edge. A huge strategic vulnerability was created under the banner of free market efficiency.
And while the U.S. was perhaps complacent, other countries were playing a very different game, using active industrial policy.
Very much. Look at South Korea. Samsung is investing eye-watering sums, over $100 billion planned by 2030, to compete in both memory and advanced logic chips. The government is deeply involved. Miller notes the significance of them paroling the Samsung heir, Lee Jae-yong, specifically citing the need for his leadership in navigating the semiconductor crisis.
That shows how high the stakes are perceived there.
Absolutely. And then there's China. Beijing views achieving semiconductor self-sufficiency as a matter of paramount national security, almost an existential goal. They're pouring literally hundreds of billions of dollars into state-backed companies like SMIC and YMTC, trying desperately to catch up despite repeated setbacks and the chokehold the U.S. is trying to put on access to technology like EUV machines. For China, this isn't just economics. It's about challenging U.S. hegemony.
So faced with this intense competition and the dawning realization of the supply chain risks, what's happening back in the U.S.? What about Intel, the former champion?
Intel is in the fight of its life. After years where they lost their manufacturing edge, fumbled transitions to new process nodes, they brought back Pat Gelsinger as CEO.
Yeah.
He's an old Intel hand, a protege of Andy Grove.
And his plan.
It's incredibly ambitious and incredibly expensive. He's basically betting the company on regaining manufacturing leadership. They're investing massively in new fabs in the US and Europe, and critically, they've placed huge orders with ASML for the next generation of EUV machines, the high-end EUV tools.
Trying to leapfrog the competition by mastering the newest tools first.
That seems to be the gamble. It's hugely risky, but the stakes are immense. As Miller points out, if Intel fails to regain competitiveness at the leading edge, there might be no American company capable of manufacturing the world's most advanced processors. The U.S. would be entirely reliant on Taiwan and South Korea.
Finally, beyond who makes the chips and where, the very nature of the chips themselves is evolving, right? Moving away from the general purpose model Intel dominated.
Yeah, that's a fascinating trend. The general-purpose CPU, the workhorse that powered the PC revolution, is still important, but it's being increasingly complemented, or even displaced in some areas, by specialized chips.
Like the NVIDIA GPUs for AI we talked about.
Exactly. Or Google's custom TTUs, tensor processing units, designed specifically for their search and AI algorithms. Apple's A-series and M-series chips. Chips designed for specific tasks often perform those tasks much faster and more efficiently than a general-purpose CPU.
So are we heading towards a future with lots of different specialized chips?
It looks that way. Some researchers talk about the decline of computers as a general-purpose technology, maybe a future divided between a fast lane of custom high-performance chips for specific applications and a slow lane of more traditional general-purpose chips for everyday tasks.
That's an interesting paradox, though. The hardware gets more specialized.
But those specialized chips, especially the AI accelerators, are enabling software, the AI models themselves that are becoming incredibly general-purpose, able to tackle a wider range of tasks than ever before.
Wow. Okay, that's been an absolutely incredible deep dive into this hidden world. Just to quickly recap the main threads from Chris Miller's Chip War.
Sure. First, we saw the chip industry was really born out of Cold War military needs. Sputnik was the catalyst. Defense spending fueled the early innovation and manufacturing scale-up.
Second, the relentless drive for lower costs. Moore's Law pushed assembly and eventually advanced fabrication offshore, primarily to Asia. First, Japan challenged, then manufacturing dominance consolidated heavily in Taiwan and South Korea, often with strategic security goals in mind for those host nations.
And third, the result today is this hyper-globalized system that's also dangerously concentrated around a few key companies and locations. TSMC for advanced fabs, ASML for the critical EUV tools. This concentration has become the central vulnerability in 21st century geopolitics, especially in the U.S.-China relationship.
It's really powerful to think that this whole story, this exponential curve of progress where a transistor now costs maybe a millionth of what it did in 1958, it was fundamentally driven by that raw, almost primal entrepreneurial spirit. Miller quotes that Fairchild Employees Exit Survey.
I want to get rich.
Yeah. That drive, that desire for profit and success built Silicon Valley's innovative culture and powered Moore's Law for decades.
It absolutely did. The decentralized competition, the willingness to take risks, that was the engine.
But now, given the sheer strategic importance, the concentration in Taiwan, the aggressive state-backed industrial policies we see from competitors, here's the final thought. Can that original free market entrepreneurial drive the get-rich impulse actually survive in an era where national security seems to demand absolute state control over this critical, now highly centralized technology?
That's the fundamental tension, isn't it? The clash between the original capitalist dynamic and the new geopolitical imperatives. A question being fought over right now in policy debates in Washington, Beijing, Brussels, Taipei, everywhere.